Hi everybody and welcome back to NE 630 Nuclear Reactor Theory. So last time we were in the same business doing the solution for the diffusion equation in infinite and finite mediums where you have a non-multiplying medium, meaning there is no fissile material. Last time we discussed the kernel and we showed that the kernel is a useful technique if you will be able to calculate what's the kernel in finite or infinite system. You can use the kernel to get a value of the flux, to estimate the flux in the finite or infinite system by just integrating the source term over the flux, and then you integrate over the space that you have, whether it is infinite or finite. And when we discussed the kernel, we stated that the kernel is just the flux at a point, let's say x, as a result of a source, unit source, present at point x prime. So just bear in mind that the source is unity when you calculate the kernel. So if you try to calculate a flux at point x prime as a result of, or at point x as a result of a unit source at x prime, this is the kernel, and you can use it to calculate the flux at any distribution. So today let's talk about the neutron diffusion length. So neutron diffusion length. We stated before that L is nothing more than sigma absorption over D. And we knew that D is 1 over 3 sigma scattering or sigma transport, if you want to be more exact. So it will be sigma transport. And the units of D is centimeter, and the units of sigma is 1 over centimeter. So this is, it will be D over sigma then. So this is D over sigma absorption. So this is 1 over centimeter, and this is centimeter. So the units of L is centimeter. Now, how we will calculate an average value, or how we will calculate the diffusion length. So again, as we just stated before, if you have a neutron like here, it makes a collision, then it's scattered here, another collision, scattered here, another collision, this is the next scattering point, and so on, until you reach to here and you get absorbed here. So let's say this is the absorption, and you started here. So this will be the average R. So how to calculate this average R? So this is, let's say, the first scattering, the second, the third, the fourth, the fifth, sixth, and this is the, we call it the crew flight distance. Crew flight distance. So this is R. R prime or R here is the crew flight distance. So how to calculate this this L in terms of the crew flight distance? So if we look at a point source in the center here, and then we will look for a spherical shell at a distance R from the center. And the thickness of this spherical shell is nothing more than dr. So now we can get the R square average by just averaging 4 by R square dr, and this is what? 4 by R square dr? No, it's 4 by R square dr. This is the volume of this spherical shell. The volume of the spherical shell is 4 pi r squared dr. When you multiply this by sigma scattering, sigma absorption, multiplied by phi, this will give you total number of absorbed neutrons inside the spherical shell. Yes? So if you in order to average r square, we will do this averaging process, 4 pi r square dr phi sigma absorption. So what you are doing here, if you remember, the averaging process is you just average over a probability function. Yes? So here, this is the weighting or probability function for us. 4 pi r squared dr sigma absorption phi, and then we divide by the same. So if you remember from the definition of any average property, it is just r p of r dr divided by b of r dr. So this b of r dr is nothing more than 4 pi r square sigma absorption phi of r dr. So this is the same law here. So if you choose in a point source, for example, if you have a point source here that emit neutrons, and the neutrons go all the way in a spherical geometry, so the flux in this geometry, phi of r, we just deduced this flux several lectures ago, and it is source multiplied by e to the power of minus r over L divided by 4 pi r d. So when you use this flux substitute in this formula, you will end up with r square average, the average of r square. So let's say if you want to choose to be r square average, so this is r square average and this is r square average. And you can write the average either like this, or you can write it like this. So r square average will be just the integration from 0 to infinity, because you are in infinite system, so it is 4 pi r square multiplied by sigma absorption multiplied by the flux. The flux is nothing more than S naught divided by 4 pi d e to the power of minus r over L dr. Then you have r square again here, which is the averaging this one r square. Then you will divide this by 0 to infinity, 4 pi r square sigma absorption S naught divided by 4 pi d e to the power of minus r over L dr. So of course you can eliminate S naught and sigma naught and S naught and sigma naught, and 4 pi d was 4 pi d. Then you will end up with the integration from 0 to infinity. This is r cubed so this is r cubed e to the power of minus r over L divided by r e to the power of minus r over L dr from 0 to infinity. So let me...
Dr. Abdu?
Yeah.
How did you get rid of D?
D is constant. There is a D here and there is a D here.
Okay.
So D is constant, sigma absorption is constant, and S naught is constant. And there is R, 4 pi R, there is R here. Because the flux is R here. So R, and you have R to the power of 4 over R, so here will be R to the power of 3, and R square over R will give you R. So you will have this formula here. If you try to do this by the chain rule of integration, which gives you u dv equal to uv minus v du for both term, you'll be able to deduce that this is equal to 6L square. So in this case, L is just 1 over 6, the square root of R square average. Square root of 6. Or L square is 1 over 6 R square average. What does it mean? It means that the diffusion length is 1/6 the root mean square, or the mean is it's the mean square of the crew flight distance. So if you calculate the crew flight distance and you take the average of the square, this is R square average, then take 1/6 of this will give you the diffusion length. Now, experimentally, how to measure the diffusion length? This is a well-known experiment from the old age nuclear engineering laboratory experiment. In Stacy, he does not mention the name. He just give you the, I don't know if he mentioned the name or not, but he just give you the derivation and everything. But this is called sigma pile experiment. And what sigma pile experiment is, just you will have a pile, and pile is the name of the nuclear reactor at the very old age when Fermi invented with his colleagues the first nuclear reactor in the University of Chicago football field. Beneath it, they call it fission pile. So you just pile up the graphite blocks, and he put the fuel in between, and he used probes to do the control using the absorbers. So they usually call it nuclear pile. So this is called sigma pile. And the sigma pile is just, if you have, here is the dimension. This is Z, so this should be XY. Let's assume XY. X and Y, and this is Z. So you just have a barrel piped tank, and you fill it with water. Let's say that this is long tank. And there is a source here that you pulse neutrons at this location, and it is distributed over this cross section. So let's assume in the A direction this is 2A, this thickness, and in the Y direction this is 2B, and in the Z direction this dimension is C. And then you have a source S0 that emit neutrons isotropically, let's assume. So the equation will be still d2 phi minus 1 over L square phi equal to 0. This is the diffusion equation. In order to solve this diffusion equation, now we don't have infinite medium. So, and we have neutron distribution in the 3 dimension, X, Y, and Z. So we should expect that we will solve this equation in 3 dimensions. So this will be d2 phi by dx square plus d2 phi by dy square plus d2 phi by dz square minus 1 over L square phi equal to 0. So the way you solve this equation, of course you will have boundary conditions. So what are the boundary conditions? It's the flux at A extrapolated and negative A extrapolated should be equal to what? 0. So at any point y and z, so you are in this plane. So at any point here in this plane, at A, negative A, you should have 0 flux, A extrapolated. At any point here in the boundary, you have a 0 flux. And at any point in the top surface and in the lower surface also, you should get 0. So top surface is in the y direction. So this would be phi at x plus or minus b extrapolated, and z should be equal to 0. And in the c direction, what's the boundary condition? Flux at x, any y, but at this surface, which is c extrapolated, should be equal to what? 0. What about this surface? So the current, but this current is going this way, so the current, let's say, positive current here at x and y and z equal to 0 is equal to half the source of x and y. So the source distribution has certain distribution in x and y at z equal to 0. So this is the boundary and source conditions. So the flux is the boundary condition and the current is the source condition.
Dr. Abdu?
Yes.
Are we assuming that S naught is a uniform planar distribution?
Yeah, you can assume that if it is uniform planar distribution, so S naught will not be a function of x and y, it will be S naught. But let's assume that the source has certain distribution in this, because of course you will not have a uniform distribution except if you will have, let's say, a very huge beam tube from the reactor and your sigma bile is less than the beam, and the flux distribution in the beam will be uniform. But usually if you have a Gaussian distribution for the beam, you will have x and y and so on. So how to solve this equation? This equation, we solve it by a method called separation of variable. This is a partial differential equation, and there is a method called separation of variables. And this is very well-known method. You will assume that your flux, and you can do this with any differential equation, partial differential equation that will have this form. So if it is nabla square equal to 0, this is what? Laplacian equation. Okay, but because it does not have a 0, so even if the Laplacian equation, you can do the same, separation of variable. So you will say that I will assume that my flux as a function of x, y, and z is a function called x, which is only a function of the coordinate x, and another function y, which is only a function of the coordinate y, and a big function z, which is only a function of the coordinate z small. Then when you will do this and you will substitute here, so if you will differentiate twice with respect to x, this will give you dx capital by dx small twice square, and you will have those as constants. So when you do this and substitute, you will get y z d2x capital by dx square plus x z d2y by dy square plus x and y d2z by dz square minus 1 over L square x y z equal to 0. Now if you divide all terms by x, y, z, what you will get is, here you will eliminate y and z and you will get only x, 1 over x. So this will be 1 over x d2 x square by dx square plus 1 over y capital d2y square by dy square plus 1 over z capital d2z by dz square minus 1 over L square equal to 0. So if I did not make it equal to 0 and I write it all of this equal to 1 over L square. What this is telling me is this is d2x by dx square 1 over x. This is a function only of x. Yes? Because there is no y here. And this is a function only of y. And this is a function only of z. And L is the diffusion length. And the diffusion length is what? It's constant. So 3 independent functions. 1 in x, 1 in y, 1 in z. They are completely independent. And they are equal to constant. So each one of those should be what? Should be constant. Because this is independent from this, independent from this, and all of them, the summation is constant. So this one is vary. This x function vary with x. This y function vary with y. This z function vary with z. But the summation of the 3 is constant, so this variation plus this variation plus this is constant, this is constant, this is constant. But the 3 constants are different, of course. So in this case, I can call this one negative k1 square, and I can call this one negative k2 square, and I can call this one k3 square. Y square and y negative and y plus and so on. Why? Here is the trick. You want to look at the physics and also at the mathematics of the problem. We are solving for what? X and y. Yes? If we will be solving this equation, you will notice that I will end up with what? 1 over x d2x by what? By the x square equal to what? Negative k1 square. And 1 over y d2y by the y square is equal to what? Negative k2 what? Square. And then the last one is 1 over z d2z by dz square equal to what? Okay, look at this. If you do not put in your mind the physics of the problem, you will not be able to pick up those constants. Why we choose this one is negative, this one is negative, and this one is positive? Because of the physics of the problem. In the x-axis, this is the x-axis. Yes? The multiplication of function x and y and z will give me what? The flux. So the function x is the flux in the x direction. The function y is the flux in the y direction. The function z is the flux in the z direction. So when you multiply the 3, it will give you the flux in the 3-dimensional coordinates. Look at this. This is x. The neutrons are coming from this direction. Yes? So you expect the neutrons will go everywhere and diffuse. But because the neutron source is from here, they will start moving and there will be something like a decay, exponential decay. Yes? And because you have boundaries from here, you expect to have some distribution, like a sinusoidal distribution, like the heat. When you have a heat source and you are heating from one side, you will expect that you have a sinusoidal distribution for the heat, then a decay along the direction where, the long direction where you're heating from. You are heating from here and there is a bar. So the heat will diffuse and it will decay along the bar, but the temperature on both sides of the bar from here and here will always be what? Symmetric, will be the same, and the maximum temperature will be where? In the center. So the symmetry of the problem in the x direction and also the symmetry of the problem in the what? In the y direction entail that I have to generate a symmetric function in the x and a symmetric function in the y. Yes? So if I pick up this to be negative, the equation here will be what? d2x squared by dx squared equal to negative k squared 1x. What's this equation? Simple harmonic motion. Yes? So this gives you what? Sine and cosine. And this will be what? d2y squared by dy squared equal to negative k2 squared multiplied by y. So this is what? Simple harmonic motion. It will give you sine and cosine. What if I change the negative k1 and the negative k2 to be plus k1 and plus k2? Do you think it will give you simple harmonic motion anymore? No. It will give you exponential functions. And the exponential functions are not symmetric because they decay like this. They will not give you a symmetric function. Do you know why now we choose this to be negative and this to be negative? And why we choose this to be positive? Why? Because in the z direction, I need something decaying. So this is why I say I will pick up here a constant negative, and I pick up here a negative constant, but here I will pick up positive constant. This is very important when you to understand the physics and the math when you are trying to solve the differential equations. Because if you will memorize it, you will, oh, I forgot Dr. Abdu say this is negative or positive. Oh, I do not understand it. This is how you will forget it. If you will remember it, you have to understand what I am telling you to remember those types of solution. Okay, guys? Then now, the three summations should be equal to what? To L squared. From here, this equation is d2z by dz squared equal to plus k3 squared multiplied by z. By the way, why we choose square, square, square?
Easier to work with.
Huh? Easy to work with. Why? Because if you remember the equation d2y by dx squared, okay, equal to some constant omega squared multiplied by y. What's this? Simple harmonic multiplied by x. Sorry. This is what? Simple harmonic what? Motion, or y, by y, sorry. Or let's say if this is d2x by dt squared to make it simple harmonic motion. So, and this is what? X double dot. X double dot equal to negative omega square x. And the solution for this is what? X equal to a cosine, the square root of omega square is omega multiplied by t. This is why we picked it what? To be square, because you have to take omega square here. Otherwise, if you just make this omega, this should be what? Square root. So this is why we picked up k1 square and k2 square and k3 square. Did you understand, guys? So now, let's go and continue the solution. Now, when we will try to solve this with the boundary condition and source condition, we will notice that x will be a1 sine k1 x, and here is the square root of k1 squared, plus a2 c2 cosine k1 x. Y will be similar, will be a2 sine k2 y plus c2, this is c1, c2 cosine k2 y And what about z? It will be a3 e to the power of minus k3 z plus c3 e to the power of plus k3 z. So those are the three equations that we want to play with. Okay. Here, boundary conditions. Phi at plus or minus a extrapolated, which is x equal to a extrapolated, should be equal to what? 0. The flux on the x direction at plus a and minus a should be equal to what? 0. What function will give me symmetry? What function will give me this symmetry? I told you in the x direction, it is the flux at a extrapolated and at negative a extrapolated, my function should be equal to 0. What function will give me zeros and the border and symmetric? Cosine. So in this case I have to remove this term. A should be 0 because sine is not symmetric. And in the y direction the same, so a2 will be eliminated. Yes guys? So I will keep what? C1 and C2. Now, let's come to this one. This one, there is no symmetry. Yes, the condition is what? The flux at C equal to what? 0. So in this case, this one will give me what? 0 equal to A3. Yes? A3 e to the power of what? Minus K3 C extrapolated plus C3 e to the power of what? K3 C extrapolated. From here you will get C3 will be equal to negative A3 e to the power of minus 2 K3 C extrapolated. Yes guys? You will take this one and substitute here for C3. This will give you Z equal to A3 e to the power of minus K3Z multiplied by 1 minus e to the power of minus 2 K3 C extrapolated minus Z. Okay guys? Do you agree? Just I got the C3 from here as a function of A3. And I return it back, substitute with C3. That's it. Now, if you look at the solution now, our solution will be phi of x, y, and z is just the multiplication of those three functions. So what's the first function? C1 cosine K1A, what? X multiplied by C2 cosine K2 Y multiplied by this function here. A3 multiplied by 1 minus e to the power of blah 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 multiplied by e to the power minus K3 Z. Now, when you try to apply the boundary condition for the A, X and Y, so far we did not apply the boundary condition. We just stated that the boundary condition will entail that those two terms should be equal to what? 0, but we did not apply the boundary condition. Let's come and apply the boundary condition. So flux equal to 0, and this is equal to C1 multiplied by what? Cosine K1, and what's the X here? Yes? So flux at A extrapolated is equal to what? Is equal to 0. What does it mean? It means that either C1 is equal to 0, and this will be trivial solution, or this function is equal to what? 0. So if this function is equal to 0, when the cosine is equal to 0? The cosine is equal to 0 at what? This is 0, this is pi, so this is what? Pi over 2, and then 2, 3 pi over 2, then 5 pi over 2, and so on. So I can write this as what? I can write this as pi over 2 multiplied by 2n plus 1. So if this term here, k1 a extrapolated, is equal to this, the cosine will be equal to 0. Yes? If the coefficient of the cosine is equal to odd number multiplied by pi over 2, I will be 0. Because n here is what? 1, 2, 3, 4, and 0. So if you have 0, 0 by anything is 0, so you will end up with pi over 2. If you have 1, so this will be what? 2 multiplied by 1 is 1, plus 1 is 3, 3 over 2. If you have 3, 3 by 2 is 6, plus 1 is 7, 7 over 2, and so on. So we can do exactly the same. So what's from here, what's k1? K1 will be what? Pi over 2, 2n plus 1 over what? But should I leave it k1? It has a dependence on what? N. So I will say k1n. Now, I can do the same. I can do the same for what? For y. So y, I will get what? K2 what? I cannot say n again, because it is in the y direction. So I will say what? N. It will be equal to what? Pi over 2, 2m plus 1 over b extrapolated. So now, how I will get k3? K3 squared equal to what? K1 squared plus what? K2 squared plus what? Is from the summation of the three term equal to 1 over L squared. Yes? The first term is negative K1 squared, negative K2 squared plus K3 squared equal to 1 over L squared. Move the negative and the negative to the other side, you will get K3 squared equal to this. So now, because K1 and K2 are no longer K1 and K2, they are what? K1n squared and K2m squared plus 1 over L squared. So K3 should be what? N and M. Should depend now in N and M, because it depends on what? K1 and K2. Guys, are you with me? So now what will be the final flux? The final flux will be Kx, Y, and Z will be equal to. Now I cannot put the multiplication as before. I have to put a summation here for n equals 0 and m equals 0 up to infinity. Why? Because I have n factor, yes, and m factor. All the n's will give me will be a solution. So if you have a solution, for a differential equation, that's y1, and you have another solution that will fulfill the differential equation, which is y2. The linear combination of y1 plus y2 is still solution. We have an infinite solution of n, yes, n1, n2, n3, n4, n4 up to n infinity, and we have m solution in the y, so linear combination of both will give me a solution. So this is why I have to put what? The summation here. So now the coefficient now will be amn, nm, because also it depends on this value. So this will give me cosine k1n, and this is in the direction of x, multiplied by cosine k2m in the direction of y, but all of this is multiplied by what? E to the power of minus k3n m multiplied by what? Z, 1 minus e to the power of minus 2 multiplied by k3 N and M multiplied by C extrapolated minus Z, all of this. So this is the new formula for the flux now. So very easy, you can memorize it very well. Nice, yes? So this is the formula for what? For a flux in a three-dimensional parallel pipe with a source that's here emitting neutrons, and there is just diffusion. Yes? If I tell you, give me the formula for the flux in a three-dimensional parallel cube non-multiplying medium with the boundary condition flux at borders equal to 0 and flux at this current at this location is equal to S naught over half. So this will be the solution. How we will use this solution, how we will utilize this solution to calculate the diffusion coefficient. Where is the diffusion coefficient is taking place? It is in this K3 formula, it was here. How we will utilize this one to calculate the diffusion coefficient experimentally. So look at this. How K3 goes with N and M. K3, how it goes with N and M. K3, how it goes with N and M. K3 depends on K1 and what? And this is constant. N and M. When N and M increases to infinity, K1 and K2 will goes to what? Infinity. So they will increase. Yes? And K3 will go to what? Infinity. So if K3 goes to infinity, so for this summation, whenever K3 will increase, this term will be what? Dying. So in principle, I can eliminate all the higher order K's and keep only the K where N equal to 0 and M equal to 0. And this we will call it K300. K3 at N equals 0 and M equals 0. Because all the higher order term will go away. And then we can modify also this one. And we say, if we will be shooting neutrons from the source in this direction, but only we will be on axis. Let's assume that this parallel pipe here is now centered on axis. So the axis is here. The axis is moving on the center. The axis is moving what? In the center. So what's the value? Center means Z is this direction, X and Y is equal to what? 0. So I can simplify this a lot. And I can make it what? Now because I have only N equal to 0 and M equal to 0, I no longer need the summation, and the flux will be on axis at X equal to 0, Y equal to 0, and at any Z location will be just equal to what? A0, 0. Cosine 0 is what? 1. And the other cosine 0 is what? 1. E to the power of what? Negative K300 multiplied by what? Z. And here multiplied by what? 1 minus e to the power of minus 2 K3 C extrapolated minus Z here. If I choose my barrel pipe to be so long, to be what? So long. So long means that CEX is greater than, I am here, let's say here. So I am not at Z, let's say, I am not at Z here, or I am not near the source or near the other boundary. I am somewhere here. I put my detector in the center here to see the neutrons, count the neutrons here. So this term, CEX, will be high. It is high where? When you are far away from the what? When Z is far away from the boundary. So this term will be high. So if it is high, I can neglect it with respect to what? With the 1. So in this case, I can approximately say that phi of 0 and 0 and Z is approximately A00 e to the power of minus K300 multiplied by Z. Now, This is a formula that I can use. Yes? I can, from this formula, calculate what's the flux, yes, at several z's, and I can plot several z's far away from the border and source, and I can plot this and I can calculate those two constants, A00 and K300. So if you will be able to calculate the K300, you will be able to do what? To calculate the L. So 1 over L square will be K300 square minus pi over 2 AX minus square minus pi over 2 B extrapolated square. And this is the sigma bile experiment that you use to calculate what? To measure what?
Diffusion length?
Diffusion length. So this is how the people, they use Weber and Ben long time ago when they invented the nuclear reactors to be able to calculate experimentally in the sigma bile what's the diffusion length. It's fun, yeah, very fun. So for graphite, for example, for let me write it here, L for H2O and L for D2O and L for graphite is equal to, for light water it's 2.9 centimeter, for heavy water it's 170 centimeters, and for graphite it's 60 centimeters. Why do you think? The light water, although it's a good moderator, but the diffusion length is very small. Absorption is 4 orders of magnitude higher than the light water, the heavy water. Light water, the hydrogen isotope has almost 10,000 times absorption more than the deuterium. So this is why you have the diffusion length is a factor of what? 3, 18, something like 60 times maybe. Yeah, 60 times. Okay, guys? And the graphite is 60. So I do not have enough time to go through the migration length, which is the last part I have to talk to you about. But next time I will define the migration length, and then we'll be able to try to solve the diffusion equation for multiplying medium. The medium where you have a fissile material inside the medium, and you want to calculate how's the okay, do you have any questions? Nothing? Yeah, go ahead.
That's the diffusion like a carbon on the bottom?
Yes, yes.
Okay, thanks.
Okay, any questions? Thank you so much, and we'll see you next week. Have a good weekend.